I am Christina McCoy. I am Assistant Professor of Architectural Engineering at Oklahoma State University. When I worked at Thornton Tomasetti, I worked on a design team where we worked primarily on connection designs. So connection design is part of a very specialty part of structural engineering where you're working on the bolts, the welds, the plates that connect members together. Sometimes this is the same team as the team that designs the members themselves, like the beams and the columns, and sometimes this is a separate team. So on this project, we were working on a collegiate stadium. We were working on Tulane Stadium, actually. As I mentioned, this is a really good demonstration of what's called pass-through forces in connection design. Sometimes people call them through forces, but it's where a beam or any kind of member has a force that it transfers to its connection and actually just passes through the connection to the other side to another connection. So for instance, in a beam to girder connection, the beam will transfer its end shear to the girder, and that force is absorbed by the girder and becomes bending stress in that girder. That's not a pass-through force. A pass-through force is one where it goes actually through the connection and just to the other side and to the member or end connection on the other side. So it doesn't get absorbed, it just goes through. On Tulane Football Stadium, we had an instance where the brace frame had a lot of force going into it. It was actually the only brace frame for that level, so it took all the lateral force for a particular level. So it couldn't get all of the lateral force it needed in through the shear studs on top. So typically the lateral force gets from the diaphragm to the brace frame through shear studs on top of the beam that's part of the brace frame. Well, we couldn't fit enough shear studs on the top of the beam to transfer all that force. And so what we did is we arranged some beams in line with the brace frame that would absorb that force and actually transfer it in as part of that line as drag struts that transfer the through force through. So let me give an example. So say each beam has enough studs to absorb maybe 100 kips. So one beam, the first beam in the line of beams would absorb that 100 kips and then pass that force through its connection to the other side, to the next connection. So the next beam would have that 100 kips in and then absorb another 100 kips. That beam would then have 200 kips, which it would pass through its connection to the next beam in line, and so on until all the force that was needed to get into that braced frame was absorbed and transferred through that final connection on the brace frame beam. So it actually accumulated to be a lot of force. And so the force went along that line into the brace frame system. Usually the beams would be connected through web plates, connecting their webs so that they still serve as pin connections for this axial force. However, there was so much force, we had to connect the flanges as well. So just to handle all that force going through the connection, we connected at the flanges, which made those beams in connections have moment connections. So since the flanges were connected, they weren't moment connections because they needed to be part of a moment frame. They were moment connections because they were passing a bunch of axial force through. So that of course changed how the moment worked in the beam. And that was all handled through the way we connected and the forces that we designed the connection for. It actually changed the way those beams were designed, but it worked just fine. It was just something we needed to account for in coordination with the team that designed all the members and the team that designed the connection designs for the project.